Hello and welcome back to your Chem 4 lecture. We are moving on in chapter 6, talking about now molecular compounds. So we had a deep discussion on what ionic compounds are, how they're named. At the beginning of that, we briefly mentioned, there's a difference between ionic compounds and molecular compounds in that molecular compounds share electrons, whereas ionic compounds are simply held together by the attraction of positive ions and negative ions. So in this lecture, we're going to talk about molecular compounds and how they're named. Because ionic compounds are all about electrostatic attractions, all you have to do for their formulas, you just need to know the cation and anion. And then from there, you absolutely know the formula because the formula unit has to be the smallest ratio that balances charges. That's not the case with molecular compounds, though, because in molecular compounds, electrons are going to be shared between atoms. And because of that, basically, the only limitation on sharing electrons is how many ways you can imagine getting each of these atoms 8 electrons. And sure enough, there's many, many ways that you can do that. So we have to come up with a different system of nomenclature for molecular compounds. Now I have good news and bad news. The good news is this method is really easy to learn. I think you'll do great on this method. The problem is you may be tempted to apply this method to ionic compounds. So what I want you to do is make sure we're going to try to split these up very, very clearly so that you don't get this confused. But I want to make sure that what we learned about ionic compounds is still going to apply to ionic compounds. We're talking about a different type of compound now and a different type of system for naming that. And that's what we're going to focus on now. Okay. So remember, molecular compounds form when atoms of 2 or more nonmetals share electrons and form a covalent bond. So like, for example, nitrogen and oxygen, 2 nonmetals, when they're combined together, they have to be in a molecular compound. They can't be ionic because neither of them is going to be able to take away the electrons from the other. And then once we form this sharing of electrons that we call a covalent bond, remember, these outermost electrons are called valence electrons. So when they're shared between 2 atoms, they're covalent between the 2 atoms. That's why we say it's a covalent bond or a shared bond. This is in contrast to an ionic bond, which, remember, an ionic bond is going to be purely based on charge. Once this covalent bond forms, that's when we have a molecule. So that's why when we talk about a molecule of water, what we're saying is we have a molecule of 1 oxygen atom with bonds to 2 hydrogen atoms. That's H2O, hence the word molecule. Okay, so here's what we do to name molecular compounds. Again, I'm going to tell you, this is a much easier way to name things than the ionic nomenclature, but don't be tempted. This is only going to apply for molecular compounds. That is, compounds of 2 or more nonmetals. So the way that you do it is you name the first nonmetal, and then you have, and then you name the second nonmetal. The second nonmetal is going to be the first syllable of the name with the IDE ending. So just like oxygen becomes oxide, it still, if it's the second element, would become oxide. And then we apply the prefixes. And the prefixes just vary depending on the number of each that you have. So if you have 1 atom of something, it's a mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. Okay, so one thing to note here, so there's a few exceptions to this, which is this prefix, mono. Mono is only going to be used when it's the second element. So we just, by convention, don't use mono as the prefix for the first one. For example, NO2. N is nitrogen. O is oxygen. So we have one nitrogen, 2 oxygens. So you might think, oh, it's mononitrogen dioxide, dioxide. But in fact, we just drop the mono when we only have 1 of the first element. Think carbon dioxide. Carbon dioxide is CO2. Carbon 1, oxygen 2. And here this gives a way to distinguish between these molecular compounds that can have weird combinations that we aren't as able to predict as we are for ionic compounds. NO2, NO3, both compounds that occur in nature. And we need to know because they have very different properties. So this one is nitrogen dioxide. This is nitrogen trioxide. What else do I want to say here? Oh, if you have, so this is kind of a bad example, but if you have, for example, 5 oxygens, the prefix for 5 is penta. So you might say pentaoxide, but just by convention, we drop that A and it becomes pentoxide. So we get rid of that A. Similar, CO is carbon monoxide. It's not monooxide. You drop that first O and it becomes, again, carbon monoxide. Yeah, and then don't worry about this one. This is, you should use the mono as the second one. Okay. So what are the molecular compounds that we know about? Well, CO2 is a very important one, obviously. It's carbon dioxide. That's what's responsible for carbonation in your beverages. It's what makes up dry ice and a lot of different fire extinguishers. Carbon disulfide is a solvent that can be used for a lot of different things, but including the manufacture of various polymers like rayon. N2O is dinitrogen monoxide, and that's an anesthetic or laughing gas. NO is a stabilizer and a biochemical messenger in cells. SO2, sulfur dioxide, is used for preserving fruits, et cetera, et cetera, et cetera. Okay, so let's go ahead and do an example here. Let's name the molecular compound NBr3. First off, let's pretend that we don't know if it's molecular or not. So how would we be able to recognize that this is a molecular compound? Well, the big difference is here, identify the types of elements that you have. You have N and Br. N is nitrogen, and that's a nonmetal. Br, well, that's bromine, and that's also a nonmetal. So since we have 2 nonmetals combined, that means that we have a molecular compound. Okay, next up, how many of each of them do we have? Well, we only have 1 nitrogen. So we might think to put mono here, but of course we know we're not going to put mono for the first element. So we're just going to use nitrogen. And then bromine is our second element. So we're going to change it from bromine to bromide. And we have 3 of them. So we use the prefix tri, nitrogen tribromide. So that's all you have to do. Okay, so now it's time for the sample exercise. So hopefully this started to make sense. Again, it's a relatively straightforward. We don't have nearly as many examples of these just because it's such a straightforward thing. But let's go ahead and give it a try. Try on sample exercise 13. Pause the video now, and when we come back, we will take a look at the answers. So go ahead, pause. Okay, let's say that we're back here. So we have A, SiCl4. SiCl4 has 1 silicon, so silicon first. Chlorine is the second element, that's chloride, and we have 4 of those. So it becomes silicon tetrachloride. Next up, P2O5. P is phosphorus, O is oxygen. Oxygen is the second element, so that becomes oxide. We have 2 phosphoruses, so diphosphorus with 5 oxygens, pentoxide, diphosphorus pentoxide. Finally, Cl2O7. We have 2 chlorines in the first spot, so that's dichlorine. We have 7 oxygens in the second spot, that becomes heptoxide. Okay, so let's go ahead and do it one more time. Let's go ahead and write the name for each of these molecular compounds, A through D. Pause the video one more time, work on your sample exercise packet. When you unpause the video, we'll go through the answers. Okay, so A is CO. That's a combination of 1 carbon atom with 1 oxygen atom. So the first one's carbon. We have 1 oxygen, so that becomes monooxide or carbon monoxide. Oops. Yeah, okay. I'll talk it through rather than going through step by step so that you can kind of hear how I think about it, and hopefully that helps you. B, we have 2 nitrogens and 1 oxygen in the second step. So this should be dinitrogen monoxide, or as your book would say, dinitrogen oxide. C, we have PF3, P is phosphorus, F is fluorine. So, it's going to be 1 phosphorus, so phosphorus trifluoride. Okay, and then D is CCl4. That's one carbon followed by four chlorines. So that's carbon tetrachloride. Looking at the answers here, carbon monoxide, dinitrogen oxide, or I think you should say dinitrogen monoxide here. PF3, phosphorus trifluoride. CCl4 is carbon tetrachloride. Okay, now how do you write formulas for these molecular compounds? Well, it's just the reverse process of what we talked about. So we're going to write the formula for the molecular compound diphosphorus pentoxide. Now, I bet you can already do this, but let's go ahead and take a look at it first. So the first thing that you want to do is identify which two elements are involved in the molecular compound. Diphosphorus pentoxide. Well, phosphorus clearly means we have phosphorus, P. Oxide means that we have oxygen, O. How many of the phosphorus atoms do we have? Well, di means that we have 2. How many of the oxygens do we have? Pent means 5. So P2O5 for diphosphorus pentoxide. Okay, why don't you go ahead and give it a shot here? Sample exercise number 15. We have, give me the correct formulas for each of them. Phosphorus pentachloride, dinitrogen trioxide, and sulfur hexafluoride. Pause the video here, and when you come back, we will take a look at the answers. So pause. Okay, let's assume we're back now. So each of these times, what you do is try to identify which elements there are there. So first up, phosphorus pentachloride is a combination of phosphorus and chlorine. Dinitrogen trioxide is a combination of nitrogen and oxygen. Sulfur hexafluoride is a combination of sulfur and fluoride. Next up, then we try to figure out the subscripts. Well, penta means 5, so we have 5 chlorines for the first one. There's no prefix for phosphorus, so it's just one of those. Dinitrogen means 2 nitrogens. Trioxide means 3 oxygens. And then finally, hexa means 6, so there must be 6 fluorines to 1 sulfur atom. Okay, so now in the wild, when you encounter these compounds and you're asked to name them, like on the test, for example, I won't be necessarily telling you, oh, this is a molecular naming, oh, this is a ionic nomenclature. Instead, you're going to have to identify that for yourself. So the way that you can do it is you'll know that a compound is ionic if the first element in the formula or in the name is a metal, or it's the polyatomic ion ammonium. That's an indication that we have a cation first, followed by an anion. K2O, for example, K, potassium, is your first element. And that means that potassium, of course, being on the left side of the periodic table, is a metal. So it's a combination of a metal, potassium, with a nonmetal, oxygen. So this is going to be an ionic compound. And so it's potassium oxide. Now it's going to be molecular if that first element is instead a nonmetal. Note, again, the big exception here is if you have your ammonium cation. Just the ammonium cation means that it's an ionic compound. So for example, N2O, which looks similar to K2O, but is a very different compound. N is a nonmetal, and that means that we're going to name it using molecular nomenclature. So it's dinitrogen monoxide. Okay, so here's our big flow chart. We've made it all the way through this flow chart for how to name chemicals. So again, you want to be able to identify ionic versus molecular. Molecular is going to be just with 2 nonmetals. Ionic is going to be anytime you have a metal with a nonmetal, or if you have, a combination of polyatomic ions as well. Yeah, okay. So here we go. So let's go ahead. We're going to mix some of them together, and then we'll walk it through when we are ready for it. So again, this is a mix of ionic and molecular compounds. What I want you to do is now pause the video, give it a shot, A through E. Try to name all of these as the correct nomenclature, whether it's ionic or molecular. Does that make sense? So first, classify it ionic or molecular. That tells you how you're going to name the compound. Go ahead, pause the video now, and when you come back, we will take a look at the answers. Go ahead, pause. Okay, let's take a look. So SO3 is a combination of sulfur and oxygen, which is which means we have 2 nonmetals together. okay? And that means that it's got to be molecular. Then to name it, it's got to be, we have 1 sulfur and 3 oxygens. Sulfur comes first, so that's just sulfur, followed by 3 oxygens, trioxide. So sulfur trioxide. Okay, next up we have BaCl2. Well, Ba is barium, and that's a metal. It's a combination of a metal and a nonmetal, so that's an ionic compound. Barium is a group 2A metal. It always forms a 2+ ion. So we know the name of the cation is just barium. Chlorine, being a nonmetal, always forms the Cl- ion, which is the name chloride ion. So we just call it barium chloride. Okay, here's a tricky one. Number C, we have NH4 3PO3. Now, in this case, NH4 is ammonium, which is the positively charged polyatomic ion that we had to learn about in the last lecture. And it always has a 1+ charge. So ammonium is the cation. That means that this is going to be an ionic compound for sure. Then we're left with PO3 with a 3- charge. That matches phosphite. So the name of the compound is ammonium phosphite. Okay, next up, we have a combination of copper, carbon, and oxygen. Let's go ahead and take a look. Well, the first element is a metal. So that's a pretty good indication that we're going to have an ionic compound. And sure enough, we have CO3 on the back end. CO3 is carbonate, right? CO3 2- is carbonate. That's one of the ones that we have to memorize. Maybe you haven't had them totally memorized yet, but of course you can have your cheat sheet until we get to the test. So copper, on the other hand, to balance the 2 negative charges from carbonate, has to have, each of them have to be +1. So this is the copper 1 ion. This is carbonate. So the answer has to be copper 1 carbonate. Finally, N2O4 is a combination of nitrogen and oxygen, which is 2 nonmetals. So it's a molecular compound, like we say. Now to name it, we have 2 of the nitrogens, so that's dinitrogen. We have 4 of the oxygens. So tetraoxide becomes tetroxide, dinitrogen tetroxide. Okay, so that ends our nomenclature section. Now that we know how to name these compounds, now we're going to talk about some of the important properties of them. And as it turns out, the most important thing we can learn about a compound in order to predict its reactivity and the way it interacts with other molecules is going to be its electron structure, the way that the electrons are shared in the molecule and whether any of them are unshared in the molecule. So that brings us to the Lewis structure here. So now we talked about Lewis structures briefly, Lewis dot structures, that is, when we were talking about valence electrons in the last chapter. So remember, we have aluminum at 3 valence electrons. So to draw the aluminum Lewis dot structure, we give it 1, 2, 3 dots. And that can go up all the way to, for example, neon, which has 8 valence electrons. So we give 1, 2, 3, 4, 5, 6, 7, 8. And that's our filled noble gas octet. So these Lewis structures that we're about to draw are going to be very similar to what we've seen here for this. We're just going to make sure that now, not only are these electrons going to be assigned to one atom, they can be shared between atoms. Okay, so again, review of covalent bonds. Molecular compounds form when atoms of 2 or more nonmetals get together, they share electrons and form a covalent bond. In other words, a valence electron comes 1 from each nonmetal and comes in the middle and forms a bonding pair of electrons, which is 2 electrons. Now, the reason that we do that is, I think we'll show you here basically, is stability. So what we're going to show you is basically the stability of that forms when 2 hydrogen atoms come together and form a pair of electrons in the hydrogen molecule, which is H2. Okay, so here's what happens. Hydrogen atoms themselves have just 1 valence electron. And for them to be stable, remember, a stable configuration is going to look like its nearest noble gas. What's the nearest noble gas to hydrogen? 1 over is helium, right? Helium has 2 valence electrons. So in order for the hydrogen atom to be stable, it needs to have 2 valence electrons. Now, each of them being the same, neither of them is going to pull the electron off of one or the other. But what they can do as they come closer together, they can actually arrange to share their electrons. So rather than this one having one and this one having one, instead they share two in the middle and form this molecule here. Now it's difficult to see on this slide, but what I want to show you is the way this works is kind of like a Venn diagram. You have your hydrogen atom on each side, and then in the middle is the pair of electrons that they share between. So now, remember, helium would look like this, right, with two valence electrons. So helium, these hydrogens now each look like the helium that's the stable noble gas. Now, normally we would call it an octet. For hydrogen, again, it only has two electrons, so octet doesn't really make sense. It's called a duet, but that's not gonna, we don't need to memorize that or anything like that. Okay, now why is it that it gets more stable as this chemical bond forms, right? This is like one of the big important parts of the universe. This explains basically all the chemical reactions that occur. And the reason is, remember, electrons are negatively charged. So if electrons are negatively charged, they're going to be attracted to positively charged nuclei. Now here, this electron has one nuclei that it's attracted to. That's good, right? But look at the electron down here. Now all of a sudden, not only is it attracted to this nucleus, it also is attracted to this nucleus. So the more positive charge that it's near and has to itself, or shares, I guess, with another electron, the more stable it's going to be. Just like a ball rolling down the hill, electrons are always rolling to find the lowest area of potential energy. And in this case, it's just think like a magnet, basically. Like a magnets are going to attract from a distance, right? Well, the positively charged nucleus is going to attract the electron from the distance as well. And then we can form these stable arrangements that allow for the sharing of electrons over a greater space. Okay, so this right here that we just did, this is what we call a Lewis structure. And this is going to be an important part of the last half of this chapter. Okay, so the Lewis structure is going to show the valence electrons of all the atoms arranged in a molecule to give octets, except for hydrogen. Hydrogen will only ever have two electrons. Because again, its nearest noble gas is helium, which only has two electrons. The number of electrons a nonmetal atom shares and the number of covalent bonds it forms are usually equal to the number of electrons needed to achieve that noble gas arrangement. For example, look at oxygen. Oxygen is two electrons away from a noble gas arrangement. That's why when it forms an ion, it forms the O2 minus ion. So if we were to do the Lewis dot structure for oxygen, neutral oxygen, it would look like that. Okay, now when it forms an ion, you just add two electrons in. One of them goes up here, the other one goes down here, and that gives you a filled octet. And when you fill that octet, now you have a 2 minus charge. So this is the oxide ion. But that's the thing. This is not the only way that this can occur. Think instead, what if instead of those electrons, so we've got our other oxygen here. What if instead we had two hydrogens? Well, each of these hydrogens has an electron, right? So what if these guys get closer over here and decide, oh, hey, you need an electron, I need an extra electron. Why don't we go ahead and share these electrons that we have to form a full octet? Now, all of a sudden, oxygen has its 8 electrons. This hydrogen has its 2 electrons, and this hydrogen has its 2 electrons. Okay. Now, these two dots that form here, like the center of our Venn diagram, these are what we call bonding pairs, because they're pairs of electrons that are shared between 2 or more atoms, or 2 atoms. Let's just keep with 2 atoms. These over here that are assigned only to 1, these are lone pairs. And those are kind of on the outside over here. Okay, so now let's go ahead and take a look at some Lewis structures and how we can draw them. So for example, fluorine. So this fluorine is going to form a bond just like what we saw with hydrogen and what we just did with water right now. Each fluorine atom wants to have a full octet of 8 electrons. But unfortunately, they start out with just 7 valence electrons. So each fluorine atom individually is unhappy. However, if these 2 fluorine atoms were to get together, this one gives up this electron. This one gives up this electron. All of a sudden now, all of a sudden now, they can form a bonding pair between them. And between the two, look at our Venn diagram one more time. The right one has 8 electrons. The left one has 8 electrons. Now, this bonding pair here can be really difficult to see when we draw these structures. So just so you know, sometimes we'll write it like this, or this is the way that we're going to do it in the future. The bonding pair becomes this stick, and that stick represents a covalent bond. Okay. Now this explains the diatomic molecules that we were talking about before. We have hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Boy, I can't remember if I told you this one before. I think this is the first time I've mentioned it, but there are 7 of these diatomic elements where the element exists only as the molecule. So when we say hydrogen, we don't mean a hydrogen atom. Instead, when we say hydrogen, we're talking about H2 gas. And there's 2 ways that you can remember it. The one that I remember from high school was always think of Dr. Hoberfinkel. Dr. Hoberfinkel will remind you of the 7 elements that are diatomic. Now, for those of you that are over 21, anyone under 21, go ahead, close your ears. But for those of you who are over 21, you can think of this. The mnemonic is, hold on. Have no fear of ice cold beer. Or, okay, if you're under 21, go ahead, open your ears again. You can think, have no fear of ice cold beverages. Either one totally works. And with that mnemonic, that'll remind you, these are the 7 that always form a diatomic molecule rather than existing as atoms. Okay, and again, the reason for that is going to be explained by what we're about to see. Okay, so here's what we want to do. If we want to draw a Lewis structure, we're going to start from drawing the Lewis symbols of each of the elements. So for example, carbon has 4 valence electrons. So carbon, we know, has 4 valence electrons. It's in group 4A. So we do 1, 2, 3, 4. And then we have 4 hydrogens, right? So these 4 hydrogens, they're all going to each have 1 valence electron. So we have 4 of these. Now, how do we complete the octets here? Well, carbon is going to need 4 electrons total. And each of these hydrogens needs to share 1 more electron in order for it to have its complete set of 2 electrons. Remember, hydrogen is only going to have 2 electrons, whereas all the other elements that we're going to talk about are going to need 8. Well, pretty clearly what we can do is, if we take our 4 hydrogens and arrange them at the 4 sides of the carbon, each of them bringing along their 1 extra electron, like this, we can form an octet for carbon, and then a duet of 2 for each of the hydrogens. Like that. Okay, and then to draw it a little more clearly, we replace those bonding pairs with sticks so that we can see more clearly what the molecule, what the arrangement of the molecule should be. Okay, so let's go ahead and look at some of our common Lewis structures here. We already did water, we already did methane. Let's go ahead and look at ammonia as well, because I think that one's interesting. So nitrogen, how many valence electrons does nitrogen have? Look at your periodic table. What group is it in? Group 5A. Group 5A, that means it has 5 valence electrons. So that's 1, 2, 1, 2, 3, 4, 5. Okay. Ammonia being NH3 here. So that means then that we have 3 hydrogens. 1, 2, 3. Well, how can we complete a filled octet for nitrogen and filled duets for each of these hydrogens? The only way we can do it is by putting these 3 hydrogens on the three open faces here of the nitrogen and bringing along their unpaired electrons. So we've got that one, we've got that one, we've got that one. Now let's check it out. Nitrogen has 8 electrons in its octet. Hydrogen, this one has 2, this one has 2, and this one has 2. So everyone's happy. Now drawing that in stick form, we replace the bonding pairs with a stick like that, and the lone pair stays on the nitrogen like that. Pretty cool, huh? Okay. Now that's the simplest scenario. There's also cases that would involve a double bond. And this is going to occur when atoms share 2 pairs of electrons. And they're going to form when there's not enough electrons to complete the octets for the atoms. A triple bond occurs, again, when atoms share 3 pairs of electrons. And that is going to form again when there's not enough electrons to complete the octets otherwise. Okay, so let's go ahead and give an example here, starting with a famous molecule, carbon dioxide. So if I ask you to draw the structure for carbon dioxide, and we know that the central atom is carbon. Well, so what are we going to do? Well, if the central atom is carbon, that must mean that we've got an arrangement here where we have oxygen on either end of a carbon that's in the middle. Rather than having OOC, it has to be OCO because I'm telling you the central atom is carbon. Okay, next up what we want to do is we want to go ahead and determine the total number of valence electrons for the molecule. So the way that we do that is we've got CO2, it's O, C, O, and our total number of valence electrons has got to be 1 times carbon, which is 4, plus 2 times oxygen, which has 6, which gives us a total of 16 valence electrons. Okay, so this is what's going to be like a puzzle for us from here on. So the first thing that we're going to do is, here, I'll just show you, I'll walk it through and then we'll look at the video here, because I think it's a little distracting having these tables and stuff. You don't need to do it that formally. So we have a pool of 16 total valence electrons. The first thing that we want to do is form at least one bond between the carbon and each oxygen, because we know that this is a molecule, right? We're starting off with the knowledge that this is a molecule. So we're going to form a bond between oxygen and carbon and another between carbon and oxygen. Okay, now here's the trick. Think of this like a puzzle, and the puzzle pieces are the electrons. When I drew these 1, 2 bonds, how many electrons did I place on the diagram? Remember, each stick represents a covalent bond of 2 electrons. So that means that I took 4 electrons from our total electron pool. And if we started with 16, that means that we're left with 12. Okay, the next step is going to be to complete the octets. And in order to complete the octets, what we need to do is we're going to start with the outside elements. So that's going to be oxygen in this case. We'll start with those, and then we'll try to complete the octets for carbon at a later time. So we've got 2, 4, 6. So this is how I'm looking at it here. Put a circle around this oxygen. Let's start over here because I don't want to go too fast here. So this oxygen here has this one bonding pair that we put here, and then nothing else. So it's got 2 electrons out of its total octet, meaning that it's missing 6 electrons. In order to give it an octet, what we're going to do is give it 2, 4, 6 more electrons. Now we have to take that from our total here of 12, and that leaves us with 6 here. So now oxygen has its octet. Now let's look at this oxygen. Same problem, right? It has 2 electrons from its bonding pair. But then we need to add in 2, 4, 6 more to complete its octet. Okay, but then when we add those in, that's all of our electrons. We're down to 0 valence electrons to play with. And do you think the molecule is complete? Is this a good Lewis structure? Well, look at this carbon. Does the carbon have a complete octet? No, it doesn't. So that means that we need to do something to satisfy the octet for this carbon while not breaking the octet for the oxygens. And here's how we do it. And I'll do it here because I think, again, it's just a little confusing the way the book presents it. What we do is we take this non-bonding pair from one of the outer oxygens, and we're going to turn it into a bonding pair. Same thing over here. Okay, and what that is going to look like is rather than a single stick here between the oxygen and the carbon, now there's going to be a double stick. Like that. We keep our non-bonding electrons here and here. And now let's go ahead and assess the octets one more time. Okay, so we've got oxygen, oxygen, and carbon. Okay, this oxygen has 2, 4 lone pairs, the total electrons of non-bonding electrons. Then it's got 2, 4 bonding electrons with carbon. So that's a total of 8 electrons in its octet. It's good to go. This carbon has now 2, 4, 6, 8 electrons in bonding pairs. So that means that it's got its octet. This oxygen looks a lot like the oxygen we saw before. It's got 2, 4 bonding electrons and then 2, 4 non-bonding electrons. So that's a total of 8 electrons in its valence shell. So again, oxygen satisfies the octet rule as well. So that means our final structure is going to look like this. C double bond O, C double bond O. We get our lone pairs here, and that is our Lewis structure. So that's how we do double bonds, for example. Okay. All right. Now there's some exceptions to the octet rule that we're not going to really dive into too much in this class. But there's some things you need to know. The one we already talked about that you do need to know is that hydrogen just needs a duet of 2 electrons to get its noble gas arrangement, because again, its nearest noble gas is helium, which just has 2 valence electrons. This one's not going to come up too much, but nonmetals, phosphorus, sulfur, chlorine, bromine, and iodine can all form compounds that have up to 10 or 12 valence electrons. Sulfur as well can do that. SF6, for example, has 12 valence electrons and 6 bonds to the sulfur atom. We call that expanding the valence shell. Don't worry about that too much. It's not going to really come up until, if you were to move into the Chem 1 series, we talk about it. Okay, so those are Lewis structures. Now, once we do the Lewis structures, now we're ready to assess the electronegativity of a compound. So the electronegativity values are listed here, and the whole idea of electronegativity basically is we want to be able to determine if compounds are polar or nonpolar, because whether a compound is polar or nonpolar defines a lot of its characteristics with respect to how it behaves in a biochemical system. So this is like a really crucial part of the class, is making sure that you understand how to predict a polar compound from a nonpolar compound when you encounter them in the real world when you're working with them. So that's why we're really diving deep on this topic in chapter 6. Okay, so let's go ahead and define electronegativity first. The electronegativity value of an element basically gives the attraction of an atom for the shared electrons in a bond. Notice we said in these covalent bonds that electrons are shared, but that doesn't always mean that they're shared equally. Now, if you have 2 atoms that are the same, so you have a hydrogen atom and a hydrogen atom, they are going to share the atoms equally with one another, because they're going to share the electrons in a bond equally with one another, because they have the same charges, they have the same valence shells, so there's nothing else to worry about. However, when we have 2 or more different atoms that are bonded together, now all of a sudden, some atoms pull on those shared electrons more than others. That's why water is a polar molecule. Oxygen pulls on the shared electrons with that. Remember, let's look at the Lewis structure for water real quick. This is the one that we drew earlier in our notes. Oxygen pulls on the shared electrons a lot harder than the hydrogen does. In other words, oxygen is more electronegative. It's pulling those electrons to its side. So because of that, a charge gradient builds up. where the oxygen atom is going to have a partial negative charge, and each of the hydrogen atoms is going to have a partial positive charge. Okay, so electronegativity, that's a specific case, but that's going to kind of inform a lot of what we do here. Notice that electronegativity increases from left to right going across a period, and it increases from bottom to top. So the way that I always remember this is that fluorine is the highest electronegativity. So look at your periodic table and find fluorine. That's in the upper right-hand corner, right? That's the most electronegative element. That's the one that's going to pull on these covalent electrons the most. And electronegativity falls away from there. So it gets lower as you go to the left, and it gets lower as you go down. That's always the way I'm able to remember this trend. Metals tend to be very low electronegative. They don't want electrons very much. And nonmetals tend to want electrons. Okay, so these are a group of relative electronegativity values that have just been assigned. Basically, fluorine is defined as a 4, and then you determine based on bonds which atom is going to take the most electrons away from fluorine most of the time. So like oxygen is the second most electronegative element, and then chlorine is the third most, tied with nitrogen. And as you can see, again, electronegativity decreases as we go away from fluorine, whether that's to the left across the periodic table or down as we go down the group. Okay, so this electronegativity allows us to understand why some bonds are polar. In other words, they have a change in charge, whereas other bonds are non-polar. Here, the bond that's in the dihydrogen molecule, H2, these two atoms are the same, right? There's no way to tell these two atoms apart. So you can't, if we can't tell them apart, neither can the electrons. So the electrons are going to be equally shared between the two atoms here. This is what we call a non-polar covalent bond. And all that means is there's no buildup of charge on one side or the other. Now, let's compare now what we call a heteroatom bond, where we have hydrogen bonded with chlorine. In this case, the hydrogen electron and the chlorine electron that form the bonding pair, they do see a big difference here. They see chlorine, which is very electronegative, and they see hydrogen, which is not very electronegative. So they're going to get pulled more often towards the chlorine. Now, I wish that we got into a bigger discussion on like what bonds actually look like, because it might make more sense now. But the way you can think about it is basically these electrons are like floating around on their own in space, okay? And they're kind of floating around both sides. When you have a more electronegative element like chlorine, that means that those electrons are going to be over here more often than they are over here. I'll just erase a few of these. So it's just more likely that you're going to find these electrons next to the more electronegative element. Now, what does that mean in terms of charge? Well, electrons are negatively charged, right? So if they're showing up over here more than they're showing up over here, that means that we're building up a negative charge most of the time on this side and a positive charge over here on this side. So that's written here. Now I'll just kind of zoom in on this structure here because you see this little symbol here. This is a lowercase delta. So think of it like D for delta, but then you make a real squiggly straight line here. And then we put a plus here. This means a partial positive charge. So note, it's not like the plus in sodium ion. The sodium ion is missing an electron. It straight up has a full positive charge. This is less than one positive charge. Okay, same thing over here. For the more electronegative element, it gets a partial negative charge. So we call that delta minus. And again, it just means that it's less, it's a definite negative charge, but it's less than like a full negative charge, like on a chloride ion. Hope that makes sense. Okay, now what's the difference? How do we know when a nonpolar covalent bond is going to form versus a polar covalent bond? Well, the way that it has to be is a nonpolar covalent bond is going to form when we have a very small electronegativity difference. So this electronegativity difference should be less than 0.4. And I think we say less than or equal to 0.4. So this is kind of how you would calculate it, basically. If you have a bond between chlorine and bromine, chlorine has an electronegativity of 3.0, bromine has an electronegativity of 2.8. So the absolute value of the difference here is 0.2. 0.2 is less than 0.4, so that's a nonpolar bond. Now, a polar covalent bond is going to occur when you have a modest electronegativity difference, which is greater than 0.4. So an example here is oxygen and chlorine. Oxygen has an electronegativity of 3.5. Chlorine has an electronegativity of 3.0. Electronegativity difference, and again, you want to think of this in terms of absolute value, is 0.5. That's greater than 0.4. So that means that there's going to be an imbalance of the sharing of the electrons. Now, which side is going to be partially negative and which side is going to be partially positive? Well, the side that has the the stronger electronegativity atom, that's going to attract the electrons more, and that's going to have the partial negative charge. In this case, oxygen is more electronegative than chlorine, so that means we're going to have a partial negative charge on oxygen and a partial positive charge on chlorine. Okay, so now once we're able to identify these polar covalent bonds, now all of a sudden we need to talk about something called the bond dipole. So, okay, I've already told you how to identify the positive and negative ends of the dipole. The positive and negative ends of the covalent bond. But we can also represent this using an arrow that points from the positive end to the negative. So think of our water example one more time. Water is like this, okay? And oxygen has an electronegativity. So if we're going to find the difference in electronegativity, because we want to know if this oxygen-hydrogen bond is polar or not. The difference in electronegativity is going to be oxygen at 3.5 minus hydrogen at 2.1. And just to be safe, we'll take the absolute value. That gives us an electronegativity difference of 1.4. Well, that's a pretty strong electronegativity difference, right? So that means that our oxygen should be partially negative, our hydrogen should be partially positive. Okay, so that's one way that we can represent it. The other way that we do it is using a dipole. And the dipole is just an arrow that we draw with a little fancy thing here, and it always points to the more electronegative element. So it's going to point from hydrogen to oxygen. And the way you can remember it is this arrow is going to have a little plus sign at the end of it. So this plus sign should match up with the partial positive charge that we already drew. Again, this is what's known as a dipole. It's just a separation of charges, just in the same way that you have like a magnet that has a positive and negative end. Here we have a bond that has a positive and negative end. So it's called the dipole. Okay. Finally, you can also predict when a bond is going to be ionic, when the difference in electronegativity is going to be greater than 1.8. So just to review, if your difference in electronegativity is less than or equal to 0.4, that's nonpolar covalent. So we're predicting bonds that can form. Oh, oops, I think this is in the way. Hold on. There we go. Nonpolar covalent. Okay, now if the difference in electronegativity is greater than 0.4, but less than or equal to 1.8, then we have a polar covalent bond. And finally, if the difference in electronegativity, and let's just put this in absolute values so we don't forget, we don't want to have any negative values here. That's gonna ruin everything. If it's greater than 1.8, then now we know that we would form an ionic bond. And the way you can think about it is the more electronegativity difference there is building up, the more strongly the one element is taking the electrons away from the other until what's the logical conclusion? It just simply is no longer sharing and keeping those electrons to itself, as in the case of an ionic bond. So we can look at some that we would predict, right? Potassium and chlorine, for example, we know form potassium chloride, which is an ionic compound. And why is that? Well, chlorine has an electronegativity of 3.0. Potassium has an electronegativity of 0.8. The difference in electronegativity is 2.2. It's so great that the chlorine has ripped away the electrons from potassium, so it's not sharing the electrons anymore. Oh, okay, so this is, so this is what I just said here. Okay, yeah, and this is kind of another way of showing that here, where non-polar covalent, the electrons are equally shared. There's no buildup of charge on one side or the other of the molecule. Whereas a polar covalent bond has a partial positive and partial negative end, and an ionic bond has a fully positive ion and a fully negative ion. Okay, and this is just kind of, this is a table from your text here. Okay, all right, so that was a lot. Let's go ahead and go to sample exercise number 17. What I want you to do is, using the electronegativity difference from the chart in your book or previously in this lecture, identify the type of bond, whether it's nonpolar covalent, polar covalent, or ionic, between the following atoms. You've got potassium nitrogen, nitrogen oxygen, chlorine chlorine, and hydrogen chlorine. So we already talked about a couple of these if you were paying attention, so that saves you a little bit of time right off the bat. But if not, please pause the video now. You can look in your book, or if you have the lecture slides, look a couple slides back. We have the electronegativity chart there that you can use to determine it. Otherwise, pause the video, give me the type of bond that forms here, and then we'll talk about it more when we come back. Pause. Okay, let's say that we're back now. So potassium and nitrogen have an electronegativity difference of 2.2, which indicates an ionic bond. Nitrogen and oxygen are different by 0.5, so that's a polar covalent bond. Note here for this one, oxygen being more electronegative means that it's going to have a partial negative charge. Nitrogen would have a partial positive charge. Oh, oops, sorry. Chlorine and chlorine, of course, they have the same electronegativity, so they form a non-polar covalent bond. And then finally, hydrogen and chlorine, we talked about before, also form a polar covalent bond. Okay. That does it for this lecture. Now, in the next lecture, we're going to talk about the shapes of molecules and how those shapes of molecules can interact with one another, which is a really crucial way to understand the behavior of molecules. So go ahead, try to digest this with the Lewis structures, then we'll move on into the next lecture on how we can predict their shapes and how that's going to affect their the ways that they interact. Well, until then, that does it for today, and I will see you soon. Bye-bye.